Welcome to this walkthrough of LeetCode problem number 1054, distant barcodes. In this problem, we'll tackle the challenge of rearranging an array of barcodes so that no two adjacent elements are the same. Stick around as we explore the solution step by step and discuss the efficient strategies to solve it. In this problem, we are given an array called barcodes, where each integer represents a barcode. The task is to rearrange these barcodes such that no two adjacent elements in the resulting array are the same. The goal is to return any valid rearrangement that meets this condition. For the input, we are provided with a list of integers representing the barcodes. The output should also be a list of integers, but rearranged to satisfy the condition. Let's look at an example. If the input is barcodes equals 1, 1, 1, 2, 2, 3, one possible output is 1, 2, 1, 2, 1, 3. Notice how no two adjacent numbers are the same. This is a valid rearrangement, and other valid outputs are also acceptable as long as they meet the condition. In the first example, 1, 2, 1, 2, 1, 3 is a valid output because no two adjacent barcodes are identical. However, it's important to note that there can be multiple valid outputs. For instance, 2, 1, 2, 1, 3, 1 is another valid rearrangement. Now, let's examine another input, barcodes equals 7, 7, 7, 8, 5, 5, 5. One possible output is 7, 5, 7, 5, 7, 8, 5. This rearrangement satisfies the condition of no two adjacent numbers being the same. Similarly, 5, 7, 5, 7, 8, 7, 5 is also valid. Notice how the solution ensures that even when certain numbers appear more frequently, they are distributed in the output to prevent adjacent duplicates. For the third example, the input is barcodes equals 1, 1, 1, 1, 2, 2, 3, 3. One valid output for this case is 1, 3, 1, 3, 1, 2, 1, 2. This rearrangement maintains the requirement that no two adjacent integers are the same. Another valid output could be 3, 1, 2, 1, 3, 1, 2, 1. The problem also comes with constraints to guide us. The length of the barcodes array can be as large as 10,000, and each barcode value can range between 1 and 10,000. Edge cases to consider include scenarios where the input has only one barcode, making it trivially valid, or if all barcodes are identical, which would make it impossible to rearrange them to meet the condition. Additionally, when one barcode is far more frequent than others, we need to distribute it carefully to ensure no adjacent duplicates. Another important edge case is when the input array already satisfies the condition of no two adjacent barcodes being the same. In such a case, the solution should still return a valid rearrangement, though it does not need to return the exact same input array. This allows flexibility in the output as long as it meets the problem's requirements. By considering all these constraints and edge cases, we can ensure the solution is robust and handles a wide variety of inputs effectively. To solve the problem of rearranging barcodes so that no two adjacent elements are the same, we can consider multiple approaches, each with its own trade-offs. The first approach is a brute force method. Here, the intuition is to generate all possible permutations of the given barcodes and verify which ones meet the condition of no two adjacent elements being identical. This could be implemented with backtracking or by leveraging a library like itertools.permutations. However, the time complexity for this approach is factorial O(n), since we're generating all permutations. Additionally, validating each arrangement adds O(n) per check, leading to an overall complexity of O(n*(n). Clearly, this method becomes impractical for larger inputs due to the exponential growth in computation time. A more promising approach is the greedy frequency-based method. Here, the key insight is that the most frequent barcode poses the highest risk of adjacency violations. To address this, we prioritize placing the most frequent barcode at alternate positions, such as indices 0, 2, 4, and so on. This minimizes the chance of any two identical barcodes ending up next to each other. Using a combination of frequency counting, a max heap, and strategic placement, this approach ensures that the most frequent barcodes are handled first, while the less frequent ones fill the gaps in the arrangement. The greedy frequency-based approach offers significant improvements in efficiency. Its time complexity is O(n log k), where n is the total number of barcodes and k is the number of unique barcodes. This accounts for the heap operations and traversing the array. Space complexity is OK, as we need space for the heap and the frequency map. While this method is efficient, the implementation involves managing a heap, which adds some complexity. As an alternative, we can use a bucket sort approach combined with frequency sorting. Here, we first count the frequencies of each barcode, sort them by frequency, and then manually distribute them between even and odd indices. The time complexity for this method is O(n) plus k log k, where O(n) comes from counting frequencies and k log k is for sorting the unique barcodes by frequency. The space complexity remains k. However, this approach requires careful handling of indices during placement, which makes it prone to implementation errors. Overall, the greedy approach provides a more structured and reliable way to solve the problem efficiently. The chosen strategy for this problem is the greedy frequency-based approach. This method strikes the right balance between efficiency and ease of implementation. By using a max heap, we ensure that the most frequent barcode is placed first, reducing the likelihood of adjacency violations. The process of placing barcodes at even indices first, followed by odd indices, guarantees that no two adjacent barcodes are the same, provided the most frequent barcode doesn't exceed n+1/2 occurrences. This condition is inherently satisfied by the problem constraints. The key insight that simplifies this problem is recognizing that adjacency issues primarily arise from the most frequent barcode. By focusing on this frequency-centric solution, we can achieve a valid arrangement without excessive backtracking. This realization was crucial in narrowing down the solution space and arriving at an efficient approach. When evaluating trade-offs, the greedy approach significantly outperforms the brute force method, reducing the time complexity from O(n) to O(n) log k. This makes it practical and scalable for larger inputs. While the bucket sort alternative is also feasible, it introduces additional complexity in managing indices without offering substantial performance benefits over the heap-based solution. Ultimately, the greedy frequency-based approach proves to be the optimal choice due to its simplicity, efficiency, and scalability. It ensures that the constraints of the problem are met while maintaining a clear and structured implementation process. This solution not only guarantees correctness but also adheres to the computational requirements for handling large datasets effectively. In this problem, we need to rearrange the elements of an array so that no two adjacent elements are the same. This is challenging because we must carefully manage the placement of elements to avoid duplicates while ensuring the solution is efficient and scalable. The first step is to analyze the problem. The key here is to distribute the most frequent barcodes as far apart as possible. This minimizes the risk of adjacent duplicates. Next, we count the frequency of each barcode using a hash map or Python's counter. For example, if the barcodes are 1, 1, 1, 2, 2, 3, the frequency map would be 1, 3, 2, 2, 3, 1. After that, we use a max heap to sort the barcodes by their frequencies in descending order. This allows us to easily access the most frequent barcode, which is the one most likely to cause duplicate issues. In our example, the max heap would contain 3, 1, 2, 2, 1, 3, where each pair represents the frequency and the barcode. This setup prepares us to arrange the barcodes effectively. To construct the result, we begin by initializing an empty array of the same length as the input barcodes. Then, we use two pointers to fill the array. Starting with even indices like 0, 2, 4, we place the most frequent barcodes. Once all even indices are filled, we move to odd indices like 1, 3, 5 for the remaining barcodes. This even-odd placement ensures that the barcodes with the highest frequency are spaced as far apart as possible, reducing the likelihood of adjacent duplicates. After placing each barcode, we decrement its frequency and reinsert it into the heap if the frequency remains greater than 0. This process continues until the heap is empty. Using a max heap is essential because it allows us to always prioritize the barcode most likely to cause issues. The separation into even and odd indices is particularly effective when the most frequent barcode does not exceed half the total number of elements. These steps also handle edge cases like highly imbalanced frequencies by enforcing even-odd placement rules. For special cases, the algorithm adapts seamlessly. If there is only one barcode, such as 1, we can simply return the array. When all the barcodes are unique, the input is already valid since no adjacent duplicates can exist. In cases of highly imbalanced frequencies, the even-odd placement ensures correctness by maintaining the necessary spacing between duplicates. The primary data structures we use are a frequency map to store the count of each barcode, a max heap for efficient retrieval of the most frequent barcode, and a result array where we store the rearranged barcodes. Analyzing the complexity, the time complexity is O, n log k, where n is the total number of barcodes, and k is the number of unique barcodes. This comes from the heap operations, which take O log k for each barcode. The space complexity is O, n plus k, accounting for the result array and frequency map. These efficient structures and steps ensure the algorithm can handle large input sizes effectively. The implementation begins by counting the frequencies using Python's counter and building the max heap with negative frequencies to simulate a max heap using Python's heap. After initializing the result array with zeros, we process the heap. For each barcode, we place it at the next available index, starting with even indices. Once we exhaust the even indices, we switch to odd indices to continue placing the remaining barcodes. This ensures that the placement alternates and avoids adjacent duplicates. Each time a barcode is placed, its frequency is decrement, and if it still has remaining occurrences, it is reinserted into the heap. The process continues until the heap is empty. This guarantees that all barcodes are placed following the rules. For the example input 1, 1, 1, 2, 2, 3, we start by creating the frequency map 1, 3, 2, 2, 3, 1, and the max heap 3, 1, 2, 2, 1, 3. The algorithm then systematically places each barcode at the appropriate indices, ensuring no duplicates are adjacent. The final step is the construction of the result array. For the input 1, 1, 1, 2, 2, 3, we first place the most frequent barcode 1 at indices 0, 2, and 4. Next, we place the second most frequent barcode 2 at indices 1 and 3. Finally, the barcode 3 is placed at the remaining index 5. This gives us the output 1, 2, 1, 2, 1, 3, which satisfies the condition that no two adjacent barcodes are the same. The even-odd placement strategy ensures that the most frequent elements are spaced as far apart as possible, and the algorithm handles all edge cases efficiently. This approach guarantees a valid solution for any input, provided it is solvable, making it a robust and efficient method for the distant barcodes problem. To solve the distant barcodes problem, we start by importing the necessary modules, counter from the collections library to count occurrences of barcodes, and heap for heap operations. Inside the rearrange barcodes method, the first step is to count the frequency of each barcode using counter. This gives us a dictionary where keys are the barcodes and values are their frequencies. Next, we prepare a max heap to organize the barcodes by their frequencies in descending order. Since Python's heap is a min heap by default, we negate the frequency values to simulate a max heap. We then transform our frequency data into a heap using heap.heapify. After that, we set up an empty list called result to store the rearranged barcodes and initialize variables, preb_count and preb_barcode, to track the barcode from the previous step and its remaining count. The goal is to ensure that no two adjacent barcodes are the same as we build the result list. Now, we enter a loop that continues until the heap is empty. Inside this loop, we pop the barcode with the highest frequency from the heap, append it to the result list, and check if the previously used barcode still has a remaining count. If it does, we push it back into the heap. This ensures that we alternate between barcodes as much as possible. Finally, we update preb_count and preb_barcode to reflect the current barcode's count after it has been used. Once the heap is fully processed, we simply return the result list, which contains the barcodes rearranged such that no two adjacent barcodes are the same. By leveraging the max heap to always prioritize the most frequent barcodes, and using the logic to reinsert previously used barcodes when needed, this approach ensures that we meet the problem's constraints while maintaining an efficient solution. Here, we begin by implementing the solution to rearrange the barcodes so that no two adjacent elements are the same. First, we count the frequency of each barcode using a hash map, where the key is the barcode and the value is its frequency. This allows us to determine how many times each barcode appears in the input array. Next, we use a max heap, implemented as a priority queue, to store the barcodes along with their frequencies. The heap is configured to prioritize elements with higher frequencies, ensuring that the most frequent barcodes are processed first. After that, we initialize an array called result to store the rearranged barcodes and set up a variable previous to keep track of the barcode that was last placed in the array, along with its remaining frequency. This setup is essential for ensuring that no two adjacent elements in the resulting array are the same. Now, we enter the main loop where we process the barcodes in the max heap. We start by pulling the most frequent barcode from the heap and placing it in the next available position in the result array. If the previously used barcode still has a remaining frequency greater than 0, we push it back into the heap to be used in subsequent iterations. This ensures that barcodes are only reused when necessary and helps maintain the condition that no two adjacent barcodes are the same. After placing the current barcode, we update its frequency and assign it to previous, so it becomes the last used barcode for the next iteration. Finally, once the heap is empty and all barcodes are placed in the result array, we return the rearranged array as the solution. To solve this problem, we start with the input 1, 1, 1, 2, 2, 3. The first step is to calculate the frequency of each barcode using the counter class, which gives us 1, 3, 2, 2, 3, 1. Next, we initialize a max heap to prioritize the barcodes with the highest frequency. In a max heap, each entry is stored as a tuple with the negative count in the barcode itself, so we represent it as -3, 1, -2, 2, -1, 3. After applying the heapify operation, the heap remains as -3, 1, -2, 2, -1, 3, maintaining the order of highest frequency elements at the top. With this preparation done, we can now focus on rearranging the barcodes to ensure no two adjacent barcodes are the same. We initialize three variables: an empty list result to store the final arrangement, prev_count as 0, and prev_barcode as none to keep track of the previously used barcode. In the first iteration, we pop the most frequent barcode, -3, 1, from the heap. We add 1 to the result, making it 1. Since prev_count is 0, there's nothing to push back into the heap. We then update prev_count to -2 and prev_barcode to 1. For the second iteration, we pop -2, 2, adding 2 to the result, which becomes 1, 2. This time, we push the previous barcode, -2, 1, back into the heap because it still has remaining occurrences. The updated heap is -1, 3, -2, 1. Finally, we update prev_count to -1 and prev_barcode to 2, setting the stage for the next iteration. In the third iteration, we pop -2, 1 from the heap and add 1 to the result, forming 1, 2, 1. Since the previous barcode, 2, still has occurrences left, we push -1, 2 back into the heap. The heap now becomes -1, 3, -1, 2. We then update prev_count to -1 and prev_barcode to 1. This process continues, alternating between popping the most frequent barcode and pushing any remaining occurrences of the previous barcode back into the heap. Once the heap is empty, we obtain the final arrangement of barcodes, 1, 2, 1, 3, 1, 2. This arrangement satisfies the condition that no two adjacent barcodes are the same. Now, let's consider another example with input 7, 7, 7, 8, 8, 9. The first step is to calculate the frequency of each barcode, resulting in 7, 3, 8, 2, 9, 1. Using these frequencies, we initialize a max heap as -3, 7, -2, 8, -1, 9. To rearrange the barcodes, we start with the first iteration, where we pop -3, 7 from the heap and add 7 to the result, making it 7. At this point, we update prev_count to -2 and prev_barcode to 7. By keeping track of these variables, we ensure that the same barcode is not placed adjacent to itself in subsequent steps. In the second iteration, we pop -2, 8 from the heap and add 8 to the result, resulting in 7, 8. Since the previous barcode, 7, still has remaining occurrences, we push -2, 7 back into the heap. The heap now becomes -1, 9, -2, 7. We then update prev_count to -1 and prev_barcode to 8. The process continues in this manner, alternating between the most frequent barcode and ensuring previously used barcodes are reinserted into the heap. By maintaining this process until the heap is empty, we achieve the final arrangement, 7, 8, 7, 9, 7, 8. This arrangement avoids any two adjacent barcodes being identical. For the third example, we take the input, 1, 1, 2, 2, 3, 3. After counting the frequencies, we find 1, 2, 2, 2, 3, 2. This leads to a max heap initialization as -2, 1, -2, 2, -2, 3. In the first iteration, we pop -2, 1 from the heap and add 1 to the result, which starts as 1. We then update preb_count to -1 and preb_barcode to 1, preparing for the next step. By carefully alternating between the remaining barcodes while maintaining their frequencies in the heap, we ensure that the arrangement continues without any two adjacent barcodes being the same. In the second iteration, we pop -2, 2 from the heap and add 2 to the result, making it 1, 2. At this point, we push the previous barcode, -1, 1, back into the heap since it still has one remaining occurrence. The heap updates to -2, 3, -1, 1. This process continues by alternating between the most frequent barcodes, ensuring that no two identical barcodes are adjacent. When the heap is fully processed, the final arrangement is 1, 2, 3, 1, 2, 3, which satisfies the problem's constraints. The key insights from this solution are that the max heap allows us to always select the barcode with the highest frequency first, ensuring the most constrained barcodes are placed early. The use of preb_count and preb_barcode guarantees that no two adjacent elements are the same by temporarily holding back the previously used barcode until it can be safely reinserted. This greedy approach leverages the heap structure to maintain correctness and efficiency, making it an optimal solution for this problem. When analyzing the time complexity of our solution, the first step involves counting the frequencies of each barcode. This is achieved using Python's counter object, which iterates over the entire barcodes array once. Since we process all n elements in the input array, this step takes n time. The next significant step is building the max heap. To do this, we create a list of tuples where each tuple represents the negative frequency and corresponding barcode. Constructing this list requires iterating through all unique barcodes, which takes k time, where k is the number of distinct barcodes. After the list is created, we heapify it using the heap library. The heapify operation is linear with respect to the size of the heap, so it takes an additional k time. These two steps set up our heap for the main processing phase. Now, let's consider the main processing of the max heap. In this phase, we repeatedly extract the barcode with the highest frequency using heap pop and then reinsert the previous barcode if needed using heap push. Each of these operations takes log k time, where k is the size of the heap. Since we process all n elements in the input barcodes array and each element is appended to the result list, the total time spent on heap operations becomes n*log k. Combining all the steps, we have the frequency counting step taking n, the heap building step taking k, and the heap processing step taking n*log k. Since k, the number of unique barcodes, is at most n, the overall time complexity simplifies to n*log k. This is efficient and ensures the solution scales well even for larger inputs. Turning to space complexity, we look at the memory used by each component of the solution. First, the frequency map created by the counter object requires k space since it stores the frequency of each unique barcode. Next, the max heap requires space proportional to the number of unique barcodes, which is also k. Finally, the result list stores the rearranged barcodes, and since it includes all n elements from the input array, it takes n space. Adding these up, the total space complexity is k for the frequency map, k for the heap, and n for the result list. This gives a total of k plus n, which simplifies to n in the worst case where all barcodes are distinct and k equals n. This shows that the solution is not only time efficient but also uses memory effectively. To better understand the efficiency of our solution, let's compare it to a brute force approach. A naive solution might involve generating all possible permutations of the barcodes array and then checking each one to ensure no two adjacent barcodes are the same. However, generating permutations has a time complexity of n, which grows exponentially and becomes computationally infeasible as n increases. In contrast, The current approach leverages a greedy algorithm with a max heap to prioritize placing high-frequency barcodes as far apart as possible. This avoids the need to explore all permutations and reduces the time complexity to O, n asterisk log k, while the space complexity remains O, n. This makes the solution both optimal and scalable for practical use cases, especially when dealing with large inputs. Finally, let's analyze the best, average, and worst-case scenarios for our solution. In the best case, where all barcodes are identical, the heap operations are minimized since there's no need to rearrange distinct barcodes. Here, the time complexity is dominated by the frequency count, which is O, n. For the average case, when the input contains a typical mix of unique and duplicate barcodes, the time complexity remains O, n asterisk log k, as described earlier. In the worst case, where all barcodes are distinct and k equals n, the heap size grows to its maximum, resulting in a time complexity of O, n asterisk log n. To summarize, the dominant operation is the heap processing loop, which runs n times with each heap operation taking O, log k. This solidifies the overall complexity as O, n asterisk log k, for general cases in O, n asterisk log n, in the worst case, demonstrating that the solution is efficient across all input scenarios. When solving the distant barcodes problem, there are several common mistakes to watch out for. First, not accounting for the most frequent element can lead to invalid solutions. The frequency of the most common barcode determines whether a valid arrangement is even possible. If its frequency exceeds n+1/2, it's mathematically impossible to rearrange the array to avoid adjacent duplicates. Next, using an inefficient sorting approach is another pitfall. While sorting the array by frequency may seem straightforward, it introduces unnecessary computational overhead. A heap-based approach is much more optimal, especially since it operates with a time complexity of O, n log k, where k is the number of unique elements, compared to O, n log n, for sorting. Another issue is mismanaging placement logic, which can result in adjacent placement of the same elements. It's critical to always choose the next most frequent element for placement to maintain validity. Additionally, incorrect handling of odd and even indices can lead to invalid solutions, as odd indices are often more constrained in the greedy placement process. Finally, overlooking edge cases such as arrays with only one element, arrays where all elements are identical, or arrays with equal frequencies can introduce bugs. These scenarios require careful validation to ensure the solution works universally. Now, let's focus on insights that can help during an interview. Recognizing the pattern behind this problem is crucial. This is a variation of classic greedy problems where constraints, like avoiding adjacent placements, need to be balanced. Understanding this pattern can make it easier to tackle similar problems in the future. Additionally, heaps are a powerful tool here, as they help manage frequencies dynamically while maintaining optimal ordering. Practicing problems that involve heaps will make you more comfortable with their usage and implementation. A key insight for this problem is to prioritize placing the most frequent elements at the maximum possible distance first. This strategy reduces the risk of invalid placements later in the process. During an interview, it's also important to communicate your thought process clearly. For example, explain why you've chosen a particular data structure, like a heap, and how it helps maintain the constraints of the problem. Finally, exploring related problems like LeetCode number 621 task scheduler, number 767 reorganize string, number 358 rearrange string k distance apart, or number 451 sort characters by frequency can help you recognize similar patterns and refine your approach. There are also alternative approaches to solving the problem, each with its own trade-offs. A simpler approach involves using a greedy strategy with sorting. By sorting elements by frequency and alternating their placement, you can achieve a valid arrangement. However, this method is less efficient, with a time complexity of O, n log n. A more efficient option is the greedy approach with a max heap. This method dynamically selects the most frequent element for placement, ensuring constraints are met. It's particularly effective for larger arrays with many unique elements, as it operates with a time complexity of O, n log k. Another efficient, though more challenging, approach involves counting frequencies and directly placing elements into odd and even indices. While this method has an optimal complexity of O, n, it requires meticulous index management to implement correctly. The key takeaways here are to always consider the implications of the most frequent element, utilize heaps when dynamic ordering is needed, and thoroughly test against edge cases to ensure correctness. Each approach has its strengths, so understanding the trade-offs is essential for selecting the best solution for the given constraints. Great job sticking through to the end. To summarize, we used a greedy approach with a max heap to solve the distant barcodes problem efficiently. This problem highlights the importance of frequency analysis and prioritization in algorithm design. Thank you for watching, and be sure to check out other coding problems to further sharpen your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!